If you ever start to wonder.
If you ever start to wonder how this roller coaster works, watch this video!
Our goal is to use physics to design a roller coaster that explains how energy transformations and mechanical energy play a role in the motion of the marble.
Our project focus question is how does the law of conservation of energy explains the motion of a roller coaster and what factors in our design affect energy transformation and efficiency.
While the big question of this term is why do visionary leaders adapt?
What's the connection between these two questions?
In essence, just as a roller coaster's motion depends on efficient energy transformations, visionary leaders thrive by transforming challenges into opportunities and maintaining balance in dynamic environments. Both require foresight, adaptability, and the ability to optimize systems for long-term success.
This roller coaster applies the law of conservation of energy for it to work thoroughly.
But what is the law of conservation of energy?
The law of conservation of energy is a fundamental principle in physics that states energy cannot be created or destroyed. It can only be converted from one form to another.
So in our roller coaster, energy starts in here as the potential energy and at the highest point, and it transforms into kinetic energy as the marble moves. So at the highest peak, the potential energy is at its maximum. As the energy descends, it converts to kinetic energy.
Mechanical energy is the total of kinetic and potential energy. Our roller coaster model shows how mechanical energy changes but remains conserved throughout the ride.
We calculated the energy of the marble at 3 different points. The first point is point A, which is the highest point of the roller coaster, which has a height of 41.4 centimeters. Then the point B is the second highest point of the roller coaster, which is 25.5 centimeters. And then last is point C, which is the loop peak or the highest point of the loop, which is 10.8 centimeters, while the marble's mass is 4.2 grams. Point A, the highest point, has maximum potential energy and 0 kinetic energy. At point B, potential and kinetic energies are shared. By point C, kinetic energy is at its peak. Marble is released from the highest points until it reaches the ground. The kinetic energy found at point A is 0 joules, while the potential energy at point A is 0.017 joules. The kinetic energy at point B is 9.43 times 10 to the power of negative 4 joules, while the potential energy at point B is 0.01 joules. The velocity of the marble at point B is 0.67 meter per second. Next, the kinetic energy at point C is 5.461 times 10 to the power of negative 4 joules, while the potential energy at point C is 4.45 times 10 to the power of negative 3 joules. The marble's velocity at point C is 0.51 meter per second. The kinetic energy at half of the height is 4.05 joules. Potential energy is 8.52 times 10 to the power of negative 3. The marble's velocity at half the height is 0.439 meter per second. The kinetic energy at 1/3 of the height is 5.05 times 10 to the power of negative 3 joules. The potential energy is 0.5 joules, and the marble's velocity is 1.55 meter per second.
Work is done to bring the marble to the ground, and power measures how quickly that work is done.
Our roller coaster model has shown how energy transforms and remains conserved.
We've calculated everything from work and power to kinetic and potential energy, and now we're ready to take this knowledge to the next level.
Thank you for watching!
But wait, what does others have to say about our roller coaster model? Here's some of the feedback that we got from our friends. This model demonstrates the law of conservation of energy well, but should be more stable. It's leaning sideways. I love how well thought out this was. The marble rolls smoothly on the track and doesn't stop or slow down in the middle. This model is very good and neat.